Okay.
All right, thank you all for joining. Today we have Alessandro Alberto Trani from the University of Tokyo and the Okinawa Institute of Science and Technology. So Alessandro has finished his PhD in astrophysics at SISA at Trieste in Italy, and he's been in Japan since then. And he will tell us about free-body problems in astrophysics and beyond. So yeah, without further ado, please take it away.
Okay. Thank you very much, Yevgeny, for the introduction, and well, thank you for the invitation to give this seminar. So I like to take it from very far. So I don't know what about the background of people here. So I really start from the very beginning. And by the way, feel free to interrupt me. Let me see if this works. Yes, to interrupt me or ask questions in the meanwhile. Yeah, remote talks are already a bit difficult. The topic I will be introducing today is about the three-body problem, and especially applications to gravitational wave astrophysics. But let's really begin from the beginning of physics. So the n-body problem. So the n-body problems, again, begins being interesting from n equal 2. This is the two-body problem, of course, solved analytically, or I would say geometrically, by Newton in his Principia Philosophiae Naturalis Principia Mathematica. And after that, of course, he already moved on to the three-body problem. He discussed a bit in his book. And then many people, many other famous scientists started to investigate the gravitational three-body problem, especially with applications to the motion of the moon and the sun and the earth, especially to explain the precession of the perigee of the lunar orbit. And again, many famous people also worked out some semi-analytical solutions using mostly perturbation theory. And eventually it was just Poincaré that exposed the limits of perturbative approaches and highlight the need of a probabilistic approach to describe the evolution of three-point masses evolving through the mutual gravitational attraction. And this was mainly due to chaos. Then in the more modern era, then we start to have numerical solutions to the three-body problem. So we know the set of equations that describes the equation of motions, the equations of motion. So there was only one more analytical highlight in the 20th century from the Finnish mathematician Sundman, who actually found a solution, analytical solution for the three-body problem, but was a general series solution, was completely useless for practical purposes because it was poorly convergent. And then people started to use numerical integration, first using very rudimental tools. The first was the German Burrau, who formulates this problem here, this Pythagorean three-body problem, as this is called today. We put three-point masses on a rectangle triangle, and then these masses are at rest. We know the equation of motion. We can evolve them. So this paper actually on I think is in APJ is just a list of tables that show how is the evolution of this system. And of course, nowadays we can find videos on YouTube about this, with the trajectories of the bodies in this configuration. So this has become a kind of a test for numerical integrators nowadays. And again, this three-body problem, as it looks very simple, we know the equations of motion, was solved numerically with accuracy only in the early 70s, using some mathematical techniques to make this problem feasible from the numerical point of view. And then finally, Monaghan, who was actually statistical physicist, started to most famous probably for the invention, let's say, formulation of SPH, smooth particle hydrodynamics simulations. He started to tackle this problem from the statistical point of view. So using instead of evolving, let's say, take a set of initial conditions of the three-body problem, we take an ensemble of initial conditions and we map them to an ensemble of final outcomes. So using the assumption of thermodynamical ergodicity, he kind of solved this three-body problem using in a statistical sense. And of course, from these, there were several other theories based on the so-called statistical escape theory. And well, and then after these, many people just started to use numerical integration. So here where we stand nowadays with the three-body problem from the theoretical point of view. And of course, there are several applications of this ancient problem, 300 years old problem. And this is what I will focus today. So the main focus will be on application to gravitational wave astronomy. So in this sense, the 3-point masses I showed earlier can be representing physical system with this triplet of black holes. And I will be focusing on these two papers of mine, and which are focused on the three-body problem into different configuration, either chaotic three-body problem evolution or evolution of hierarchical stable systems of triples. And maybe I could mention these other two topics here. These are other papers either in preparation or done together with other students. But it's a remote talk, so it's very difficult to keep up the attention. So I will maybe mention only if there is time. Okay. Again, I think you're doing the timekeeping, right? So please let me know when I have 10 minutes left. So the main question of this talk is, where do gravitational waves events come from? And one way to produce gravitational wave sources I will show you later is three-body encounters in stellar clusters. The other way is from hierarchical triple system that can form in open cluster, again, dense stellar environments that we have in the galaxies. In this way, we have two kinds of triples. One is hierarchical, non-hierarchical triples, like three-body encounters in stellar clusters. You see this cartoon on the left. You have three masses. They roughly occupy the same region in space. They usually evolve chaotically and very violently through gravitational interactions. And then we have hierarchical triples like the Earth, Moon, Sun, Moon system, or even the Alpha Centauri system, which is the closest stars to the Sun. And this is a stable system, but is nonetheless a triple and can be also involved in many processes for the formation of gravitational wave sources. Okay, so let's focus first on non-hierarchical triples, also known as three-body encounters. So how does a three-body encounter looks like? I'm showing here in this video. This is a simulation of a binary meeting a single. There is also some projection effect here. But you basically see how triple masses can interact, and when they meet quite a small region of space. Let me show it again. So you see, initially you have a binary and a single. Initially, the single is the blue one, and then we have all sorts of chaotic exchanges that basically erase the initial condition, the information about the initial conditions of this system. And after several chaotic interaction, we see that the system breaks up. There is a binary here that is exiting the box. This binary is not anymore the original one. There was an exchange between the blue and the orange particle. And this is how all three-body encounters end. So there is a breakup between the binary and the single. You cannot form any stable system with this triple interaction. So as in the beginning, we have a binary and a single meeting. At the end, we have a binary and a single outgoing. This is what happens, not just, it's not just an academic exercise. This is what happens in stellar clusters. And like global cluster, for example, we have in the Milky Way. And this is an old-fashioned cartoon on how this type of encounter. So again, you can have these encounter happening in the dense stellar cores, also of open cluster as well. These bodies can be stars, but in our case, we'll be focusing mostly on black holes. And why black holes? Is because they, well, we do know that black holes merge and produce gravitational wave events. And this, but of course, we would like to know how these binary black holes are formed. And one practical way to form binaries is through three-body encounter. So if the center of a star cluster is very dense, usually it is very dense, and thanks to a phenomenon called core collapse, if three isolated black holes meet, they can undergo a chaotic three-body interaction, then form a binary and eject a single. So here you pair isolated black holes, and then the binary might be too large for it to merge within a Hubble time of the age of the universe. So, but three-body encounter can also help in this. So if you have a binary, let's say it's too large, it might meet per body, have again a chaotic encounter, then tighten up so that maybe due to the reduced size, the final binary will be merging much quicker and maybe even in the observable universe. So these are both key processes. Usually this is also called binary hardening in jargon. And these are, again, key process for producing gravitational wave events from compact object binaries. Again, the main motivation rationale is that we do observe gravitational wave events. This was the kind of visualization how the first event looked like in 2015. This is instead how is the gravitational waveform as a the amplitude versus time of the first events. At the moment, we have 4 gravitational wave detectors online. 2 are in US from LIGO, 1 is in Italy from Virgo collaboration, and the other one is in Japan, is in the Kamioka mines, where also the neutrino experiments lie. So Ka means Kamioka, just like Kamiokan, the neutrino experiment. So this is the detector. These are the neutrino hyperkamiokan and so on. So we do have at the moment a lot of events so far, about 50. Now there is the third observational run that is now completed. The fourth observational run will begin soon. And again, from the astrophysical point of view, we would like to know how to link these gravitational wave events to astrophysical scenarios. And so how to explain these gravitational wave events and which astrophysics we can do with them. And at the moment, the main observables that we have from gravitational wave events are the following. So, of course, we have an idea about the masses of the 2 merging objects, about also the final remnant. And again, astrophysical black holes have also another parameter that characterizes them, that is spin, rotation. And through gravitational waves, we have some estimates of what is their spin and also what is the orientation of the spin vector with respect to the total angular momentum vector. Of course, we know the merger rate, which is in roughly of this order. We might know in the future about the eccentricity. Is actually quite difficult to detect in the late in spiral phase because current gravitational wave detectors just really focus on the last moments of the spiral of a compact binary. It's also unlikely that a binary keeps a very high eccentricity until that moment, because gravitational wave tends to circularize binaries. And of course, we would like also to know better about the localization, either in redshift or distance, or on the map of the sky. But at the moment, we are limited to local universe events and also we have a very coarse sky localization. So for these 2, we will probably have to wait for shorter, so larger wavelength observations. And so from this, what I'm focusing on in this talk is the spins, especially how to form the spins and especially the orientation. And what I'm talking about is this. So this is the latest distribution of spin obliquities from gravitational wave events. By obliquity, I mean is the angle between the spin vector and the normal to the plane of the binary. This is from the latest gravitational wave transient catalog 3. And this is distribution in cosine theta. So if there was absolutely no correlation between the spin directions and the angular momentum vector of the binary, you would see just a flat line. It would be completely isotropic, but as you see, it's not isotropic. There is some preference for aligned binaries. But there is also a component that is strongly anti-aligned. So this -1 means that the orbital, the spin vector is completely anti-aligned with respect to the normal to the plane of the binary. So this is quite interesting, and because we can compare this distribution to astrophysical scenarios. And the main idea of this work here, and you can see on the archive, is to produce how to produce this misalignment. So really focusing on this the tilt that we have in these in the current observations. So the main physical mechanism between this idea is to produce first generation black holes with a misaligned spin vector with respect to the orbital plane. So the first step is to produce spinning black holes, because most observations at the moment actually suggest that first generation black hole might be born with a negligible spin. So one way to do this is through tidal spin up. We know that sometimes isolated binaries enter a phase of this is called common nebula evolution, after which we have left with two cores, basically two stellar cores on a very tight orbit. Very tight orbits means that we have a very efficient tidal forces that, just like with the Earth and the Moon, can spin up synchronize the spin of the stars together with the orbital period, and can also align them. And after these two cores and collapse into black holes, we can expect that some of the angular momentum of the cores will be retained into the final remnant. But the main issue with this process is that produces spinning binary black holes with aligned spins, because tidal spin up tend to synchronize the orbit. And the second step then is to take these binaries, and if they're not just completely isolated, they might have some encounters with third bodies. And these encounters usually don't affect the spin of the black holes, which will remain fixed with the same orientation. That might affect the orbital plane of the binary. Like you can imagine that a passing black hole gets close to this binary and tilt the orbital plane. So in this way, we can produce binaries with a tilt, with the spin vectors tilted with respect to the orbital angular momentum vector. So this is the main idea. Yeah, feel free to say anything, questions or so on. And I will really just, so this is basically the main idea, the main concept. And of course, we need to verify this. What I've done so far is to run several embodied simulations, including general relativity corrections of using three-body encounters that mimic the environmental condition we have in stellar clusters like globular or open clusters. And eventually, what we obtain is this, at least at this, for binaries originating from stars of this metallicity. So what you see here is the tilt angle distribution after one encounter, one three-body encounter, as the binary plane has been tilted. This is again in cosine I between -1 and 1. Here there are several colors because we have different population of binaries. So sometimes the encounter, the original binary might survive. So the final binary is just the same members as the initial one. And this is this orange line. And otherwise, we could have also exchange binaries. So if the isolated black hole swaps with one of the binaries, and this is this blue line, as we expect, you see here, this is much more flatter, because isolated exchanges tend to, let's say, randomize a little bit more the angular momentum vector of the binary as well. So, and of course, we can compare this with the estimate from the gravitational wave catalog. However, this comparison is a bit sketchy because this angle here, this obliquity angle, is not really a conserved quantity throughout all the spiral. And what I'm showing here is the tilt angle way long before the two binaries merge. So what we can actually look at is at conserved quantities that are kind of preserved throughout all the spiral. And one of these quantities called chi effective. This is the main parameter that is extracted from gravitational wave observations. And these are some distributions that we obtain from the simulations weighted by merger rate density, a local merger rate density. And of course, we can compare this with the gravitational, at least qualitatively, with the latest catalog. So what we have at the moment is that this chi-effective parameter that can be derived from the masses of the black holes, from the spins and their orientation, is roughly peaked at, let's say, 0.1, 0.05. So it's kind of positive in peak, but also as a slope in negative chi-effective. These are anti-aligned binaries. These are mostly aligned binaries. You see, depending on several on the assumptions on the initial binary spin, initial black hole spin. So what is the black hole spin once they are born? This is quite unknown. So I simply propose 3 phenomenological models. We see that roughly the beta model, which assigns black hole spin at birth about 0.1, 0.2, it can reproduces the basic features of the observation. So a positive peak in the chi-effective distribution, but also a negative. So this positive peak corresponding to aligned binaries in general, and a negative tail corresponding to anti-aligned binaries. So this is one of the few models that can, few scenarios that can actually reproduce these the shape of this chi-effective distribution. Because again, we start with aligned binaries and then we misalign them through three-body encounters. While, for example, isolated binary evolution can mostly only produce positive chi-effective. And again, this is the summary for now. If you have more questions later, I'll be happy to reply, or also show additional slides or details. And for now, the main takeaway is that three-body encounters can tilt the orbital plane of binaries. And this can actually misalign the spin vector of these black hole binaries. And this might be seen in gravitational waves. Again, there are several caveats with this scenario. For example, the expected merger rate is quite low with respect to what we see nowadays, because the black holes post-common envelope binaries are usually very tight. Tight binary means that there is more cross-section. Small cross-section means that having likelihood for an encounter is quite low. But anyway, these are based on many assumptions, so there are more details and caveats in the paper. With this, if you have more questions, no more questions on this topic at the moment, let me go forward towards another kind of triples, so hierarchical triples. And as I mentioned earlier, hierarchical triples are very different with respect to the three-body encounters I shown earlier. In respect, we have an isolated binary. Well, we have a binary here that is orbited by a tertiary body here. So this configuration is usually stable. We can define the usual orbital parameters for both the inner orbit and the outer orbit, so same major axis of the orbit, eccentricity, and also these two inner and outer orbits might have a mutual inclination. So, and these triple systems do exist in the universe. These are, for example, this is a picture of the closest stars to the sun, Alpha Centauri, and A and B and C. This is also called Proxima Centauri because it's the closest star to the sun. Of course, these three stars are on are orbiting each other. So one day, actually, I think will be B, the closest star to the sun after several thousands of years. So these systems are actually common in the universe, and we can expect that, and especially massive stars are common in triple systems. So we can expect that some of the black holes that will be produced at the end of their lives will be found in triple systems. So how actually triple system evolves with respect to isolated binaries? So the main addition is that we have a third body that might perturb gravitationally the inner binary. And if you ignore all other non-gravitational processes, the main way these systems evolve is through angular momentum exchanges between the inner and the outer orbit. And these angular momentum exchanges, they change the orbital parameters of the inner and the outer binary. These changes happen on a secular timescale, which means it's much longer than the orbital period of the inner or outer binaries. And these angular momentum exchanges manifest themselves as the von Siepel-Kozai-Lidov oscillations. You might maybe heard of the Kozai-Lidov mechanism sometimes. Basically, there are oscillations in the eccentricity of the inner binary, which correspond also to oscillation in the mutual inclination between the inner and outer binary. This you see in a simulation, how it looks like. And these rapid oscillations, you see there is also an envelope of this oscillation, which the eccentricity of the inner binary gets very high. So this is 1 minus the eccentricity. When the eccentricity of the inner binary gets very high, we have extremely short pericenter passages of the inner binary. This is extremely important if you have a compact object binary, because gravitational wave emission is very efficient when the two bodies get very close. So with this mechanism, we can basically accelerate the merging of binaries. And especially if you take for example, the derivative of the quadrupole gravitational wave with the 2pm gravitational wave radiation term is as the expression. So as the eccentricity goes to 1, the derivative of the same major axis really goes to crazy values. So, and this is how it looks like in a more real simulation of a triple with an inner compact object. So this is again 1 minus the eccentricity as a function of time, the inclination of between the inner and outer binary. This is the same major axis of the inner binary. So this inner binary originally had a same major axis of 1 AU. And the masses here are about 10 solar masses. So a binary with the same major axis of a separation of 1 AU, it will never merge within the age of the universe, because separation is simply too high, too large for gravitational wave radiation to be efficient. But however, we have this binary is not isolated; it's orbited by a third body. So we have these very rapid oscillations in the eccentricity, and during these short pericenter passages, gravitational wave radiation is emitted, and so you see that the same major axis of this binary slowly goes down until finally this binary merges at 25 million years. So this is how it looks like, this typical gravitational wave merger induced by Kozai-Lidov oscillations, and that's how we can produce gravitational wave events. However, of course, there is always the question how actually triple system come from. So we have 2 main mechanisms we can produce triple systems. One, again, is the natural outcome of star formation. What we observe in the universe are what we think are maybe primordial triples. So triples that were simply born from molecular gas cloud as a bound triple. But there are also another kind of triple, which are the dynamically formed triples, and this can form through 4-body interaction or few body interactions. Just like 3-body interactions, if we add 1 more body, for example, we have 2 binaries meeting, you can have a chaotic interaction, and then one body is ejected and a stable triple can be formed in this case. So this is what I focused in this paper. And especially what I did is to take a sample of triples from low mass cluster simulations, or even open cluster simulation, if you want to call like this. So the main idea is to take several simulations, n-body simulations of stellar clusters, like this one I'm showing here, even much smaller, so way less amount of particles, because these are low mass star clusters. Of course, have some physics for the stars, star evolution, so we can self-consistently model also the evolution of massive stars into black holes and the effect of supernova kicks on the dynamics and so on. And eventually, from this cluster simulation, we can form binaries, of course, dynamically form binaries, but we can also form triples. And especially this simulation was run by my collaborators in Italy. And what I found in their data set was something like 6 10 to the 4 triple systems formed, about 2 triples formed per clusters. So these are a lot of star cluster simulations. So once we obtain these triple systems, we can select triples with compact objects and then run them and evolve them until they basically merge. And my slide froze. Okay, perfect. And what I selected from their sample of triples are triples with an inner binary black hole, triples with a black hole neutron star binary, and triples with an inner black hole white dwarf binaries. So these are all the main compact objects I found in these triples. There are no, for example, binary neutron star in triples, unfortunately. And after evolving these triples, checking how many of them actually merge within a Hubble time, then after assuming some star formation rate model and also cosmological model, we can calculate what is the merger rate density that we expect from these triples, both the local merger rate density here at 0 and also the one at higher redshift. And this is what you see this is what I obtained. And in particular, the main highlight is the local merger rate, which is of the order of 0.1 per year per gigaparsec cube. This is very low, extremely low, but still detectable, given that the number of detections is going to be to increase a lot in the future. But it, of course, is marginal with respect to the current local merger rate density estimated from LIGO Virgo Kagra. So the main reason why this merger rate density is so low is that there are not many triples forming in low mass cluster. So 2 triples per cluster is quite a good number, but not many of these triples have compact objects. So unlike binaries that are way more frequently formed in open clusters, so the merger rate expected from this kind of clusters, but from dynamically formed binaries, is much higher, roughly by a factor of 100. And even though this merger rate is quite low, it could still predict some explain rare and peculiar events. Especially, we can compare the properties of these mergers. So, for example, the distribution of primary masses, or the distributions of mass ratios between the compact objects merging. Here's focusing on black holes. And since this mechanism involves quite high eccentricity, we can also compare the eccentricity during in different gravitational wave bands. So, and what we can do even more is since we have both binaries and triples from the same cluster, we can self-consistently one-to-one compare the properties of binaries and the properties of triples. And you see here in this plot, these are the red distribution are dynamically formed binaries from the same clusters, and they predict many mergers. So this is from merging black holes, and pretty many mergers at around with primary masses at around 10, which is consistent with the observations. While black holes in triples tend to have way higher masses. So one main reason for this to happen is that triples tend to have more massive black holes. And the reason is that basically more massive black hole can more easily form higher hierarchical multiples. So if we think the binary as a multiple, it's, of course, we expect that more massive objects are found in higher multiples, so triples. And also because many of these black holes are actually formed from mergers of previous binaries. So what you see here probably are many black holes they were formed from the merger of binaries, stellar binaries. Then this stellar binary collapsed into a very massive black hole. Then this very massive black hole formed a triple in a dynamical environment. So hence we can found much higher masses, even mass gap events in these black holes formed from triples. Another interesting detail is the mass ratio distribution. So currently the gravitational wave observation suggests roughly equal mass mergers. So two black holes have roughly the same masses. This is also quite consistent with a dynamical scenario in which you have basically exchanges. So you tend always to balance the two masses in the binaries, but not in this case, not for triples, because triples actually favor low mass ratios, even in black holes. So you see this distribution of mass ratio peaks at 0.1. And this is again due to the Kosalidov effect, which is enhanced when the inner binary has a mass ratio. And of course, this also has an effect on the Kosalidov evolution, also an effect on the eccentricity at different wavebands. So here we have 10 Hertz. So let's say the beginning of the LIGO, Virgo, Kagra band. And we expect that especially black hole neutron star from this scenario will have higher eccentricity, well, higher in the sense of 10 to the minus 2, 10 to the minus 10, 10 to the minus 1. And this eccentricity will be detectable at design sensitivity in principle. And also when third generation gravitational wave, ground-based gravitational wave detectors will be online, like Cosmic Explorer or Einstein Telescope. And of course, when LISA will be online, with it up in the trailing the Earth in 2034, of course, these gravitational wave events will fall into her in LISA band. So maybe also LISA will be able to detect some eccentric sources. And with this, I really finish. What time is it? Quite, yeah. Okay. I just summarize here. So I just showed that hierarchical triples form in open clusters. From free-body encounters, we can study the evolution of these triples using embodied simulations, and this mechanism called von Zeipel-Kosalidov oscillations can accelerate the merging of these binaries and the inner binaries, especially if they're compact objects, and we can then predict the population and the properties of compact object mergers coming from these scenarios. And okay, can you, if you don't have more questions or any questions, I can stop here, or just, yeah, I stop here. Yeah.
All right. Thanks, Alessandro. Let's see if there are any questions on this part. Are there any hands?
I had a question.
Yeah, go ahead.
I was a little bit confused when you said that you formed 3 triples per cluster, but then you're getting many different cluster simulations. 3 seems very low. Did I misunderstand that number?
No, it's two, actually, two triples per clusters. Yeah, it's quite low.
You're only forming two triple systems in the entire evolution of the cluster?
Yeah. Well, I would say I'm looking at the surviving triples. So something I should have mentioned is that these triples are the end of the evolution of the cluster. They're in isolation, basically, because the cluster has dissolved. So what I found that the isolated triples are two per clusters, basically.
Is that two that are still within the cluster boundary at the end of the simulation, and not including any triples that were maybe ejected out? Do you have any ejected out triples?
Yeah, these are the ejected out triples. Yeah, basically these are the ejected out triples. So, and there are no other triples because this cluster are between 300 and 1,000 solar masses. So they are basically the cluster is dissolved by the end of the simulation, which is 100 million years. So yeah, two triples per cluster.
Okay, thank you.
Well, actually, I have a follow-up question on that. Have you actually checked what actually maybe the typical number of exchanges you have until you get this final triples, or what are the average?
Yeah, this is something I would have liked to do. Unfortunately, we don't have I don't have the time resolution to follow this. So what I had since this simulation were really meant to study dynamically formed binaries, and then they were run by my collaborators. What I had, I didn't have enough snapshots in the simulation, time snapshot in the simulation, to really track the evolution of these binaries. So of the triple members. So I could not track how many exchanges do they have, and I could track, however, how many original binaries are present in the final triple. So as I showed you earlier, let me explain a little bit more. So as I showed you earlier, the main idea is that you take two primordial binaries and maybe you make them have a four-body encounter, then you form a triple. But in this process, you expect that so at least two members of this triple must be also primordial binaries. And what I found out is this is true only in half of the triples. So actually, there are many triples formed through other mechanisms that is not few body encounters of primordial binaries. And I'm not sure which mechanism could be.
Yeah, I guess one thing you can look at is maybe on the final mass ratio of the inner binaries, and if it's more equal, maybe it is an evidence that he had plenty of exchanges.
Yeah. So yes, that's true. At least for compact object triples. Let me show you. You see this gray line is the original initial one, and there are mostly, I would say mostly equal mass binaries. Yeah.
Right. So I can, maybe if other people have questions, that's fine. Otherwise, I can ask more, or we can think somebody else.
Eugenie, there's something wrong with my.
No, I think Andrew can hear you. You can ask or write me in chat, whatever you prefer.
Yes. Look, very nice talk. I like the discussion, the historical discussion, and of course you brought us right up to the. You mentioned the word Standish. He was responsible for at JPL setting up the orbital determination program way back in 1972, and of course, you got people like Chodos there and Jacobson, and that was really so important, getting a probe into the planet, into Mercury, having all these flight paths. So that three-body problem it really has been so important, probably across 150 years. And I should note also, of course, Beppe Colombo from your country, he seems to inspired a whole lot of dynamicists. It's impressive. Now, let me get towards a question. In passing, of course, we all study the restricted three-body problem. It's a really nice thing to study too. My interest is in the solar system, and in particular, at the moment, the Pluto-Charon system. We know that has a highly inclined orbital plane around the sun, So you mentioned at some point about disruption, rather tightening of binaries, but it would have been important to know for Pluto and Charon that they weren't disrupted when they got somehow, the whole thing got tilted. So that's another important problem, not just the threat of disruption if you are a binary. And of course, there are other areas like that. So it's an extremely important problem that you've covered, and I really enjoy this. Thank you.
Oh, thank you very much. Yeah, there are several applications, especially I haven't mentioned, but I have a few slides later, which mention also the important applications of three-body problem to exoplanets or solar system dynamics, of course. Yeah.
Good. Thank you.
Thank you very much for your comment.
Not at all.
Okay, I can ask more questions if nobody else.
Yeah.
All right, so I think in the last plots you actually distinguish between dynamical and triple. So just to clear, by triple you mean field triples, and dynamical you mean in clusters?
No, these are all dynamically formed triples from my simulations, and dynamically formed binaries from the same low mass cluster simulations. You see?
Okay, so what's the difference between the field blue and the red? What are the different channels here?
Yeah. So these are basically ejected binaries from the same clusters, while these are ejected triples from the same clusters. So they are all formed dynamically. Technically, this red line is not true 100% dynamically, because we have, so this open cluster simulation, low mass cluster simulation, had very high fraction of primordial binaries. So some primordial binaries might also have very little to do with the cluster and just merge by themselves. So these are basically not isolated binaries in clusters, and also including dynamically formed and exchanged binaries, and dynamical formed triples, because there was no primordial triples in the cluster, so they're all formed dynamically.
Right. I guess that leads me towards maybe the final question. Also, regarding the comparison of this channel with other channels, namely, one thing that jumps into mind is maybe you can try to compare this rate to another properties to rates of field triples, for example, because I think that now there's evidence that most massive OB stars are actually born in triples, so that could be one thing. Look maybe on field triples.
Yep.
And also, do you think it is possible to discern this model from other channels that were suggested, such as AGNs, that you have some gas, for example, or even in the same cluster, you could still have some residual gas and maybe some gas replenishment during the classification time?
So distinguishing between, so the main predictions here are, so for example, the dynamically formed binaries, you see they have very different predictions. Also, we don't expect any eccentric mergers with simply dynamically formed binaries. On the other hand, of course, there are some degeneracies of these properties with other scenarios. For example, I think an AGN scenario also favors equal mass binaries, if I remember correctly. I'm not 100% sure now. So, because you have black holes that accrete, and well, they can form mass gap also here because they're formed from merger from stars. Probably maybe I would say electromagnetic signatures, maybe, because in AGN you might have some electromagnetic counterpart. But if not, I'm not really sure how to compare. But I'm talking about the AGN scenario. Then how to distinguish dynamically formed triples from field triples, for example. I'm not. Technically, it's the same mechanism. So these are all mergers due to causality of oscillation. So the properties of the mergers are very similar in a sense. We can distinguish, for example, I had a look at the papers from the Fred Razio's group, and they take triples from from global clusters, and these triples from global cluster are very compact, of course, because there's much bigger environment than low mass clusters. So what they see is basically there is even the inner binaries in triples merge by themselves. They don't need really causality of oscillations to merge, because they are quite tight already, which is not the case for my case instead, for triples from open clusters. But yeah, the mechanism is the same, so we expect the same properties, roughly the same properties at the end. So some residual eccentricity and unequal mass ratios.
Yeah, I agree that the mechanism is the same, but maybe the initial conditions are not the same, because I guess essentially, if you just look on all B stars, they're kind of isolated to some extent, while the initial conditions that lead to a triple after a cluster has dissipated could be much more different. You could have more maybe extreme mass ratios in the triple that was assembled during the dynamical stage of the cluster.
Yeah, this could be a mechanism. Yeah, in this case, well, this is an embodied simulation. There is no gas, but yeah, it would be difficult also to estimate, I think, what could be the initial conditions of these triples from, in a more realistic environment, including residual gas. Yeah.
Okay.
So yeah, I cannot. I'm just doing some guess. I really cannot predict what could be the main difference, but definitely, yeah, the initial condition. So the main population of masses, roughly speaking.
I guess maybe just final comment that if we're looking at the slide, then yes, maybe the rates are quite low compared to the overall rates. But I guess the main thing is that actually a significant portion of them could be actually with some non-zero eccentricity during the typical frequency of the observation. Whereas if you just compare it to isolated binary or something else, you would predominantly expect circular mergers. Is that right?
Yeah, that's for sure. That's for sure with the dynamical. Yeah. For example, if they really don't need any causality oscillation to merge, then yeah, of course we expect very little eccentricity in the late stage of the spiral. Yeah.
All right. So yeah,
Okay.
we still have like a minute or two, but yeah, if there are no further questions, I think we can thank Alessandro again, and I think I'm gonna stop the recordings, and we'll have more of a less official chat.
Okay. Cool. Thanks. Yeah. Sorry, I cut it short because I didn't want to be too long. But yeah, basically.
That's fine. Yeah, thanks again. Oh, Sean, do you have a question or is it a clap? I think you raise your hand.
Yeah, just one thing. With getting the merge rate, did you take into account tides for the black hole? If that's going to dissipate more of the energy, like increasing the rate of circularization?
Can you repeat Can you repeat the question?
Did you take into account tides being raised on the
tides.
black holes?
Oh,
yeah.
No. You mean tides between the black holes, like
yes,
tidal effects? No. To be honest, I'm not very familiar with black hole tides and the way to model them, actually.
Yeah. Yeah. Okay, thank you.
So yeah, no. This is at the moment I'm using basically just gravitational wave Post-Newtonian corrections up to 2.5 correction term. Of course, I would be very happy if you're more if you are familiar with black hole tides, how this actually can be modeled. Yeah.
Not too sure about black holes.
Okay. Yeah.
Thank you.
All right, thank you. So let's thank Alessandro again one more time, and yeah, then we'll start recording.
Okay.
All right, thank you.